Okay, so a lot just happened there, right? Some pretty crazy units, but go back to that previous video, go back and watch that last minute or so where we worked through the units, watch that a couple of times. The big thing you want to know is what units would you like? Well, I've got specific volume, so I would like something in volume per mass. So I need to get down to something that is meters cubed per kilogram. A fancy trick in the metric system is if I've got kilos on top and I got megas on bottom, I'm going to have this issue later where that might not work out for me, okay? But if I'll start out with kilos on top, if I'll go ahead and convert to kilos on bottom, or if I've got megas on one side, put megas on the other, or the other way, I see a lot of people will just take everything down, like if you took this all the way down to joules and you took this all the way down to pascals, then it works out perfectly, okay? So make sure you got the same order of magnitude on top and bottom, and then yes, normally the metric system will just work out just fine. But be very careful with that, right? Because you'll get, if you just assume, oh, Steve, it's the metric system, it's going to work out. That's fine until you crash a Mars rover, literally. That's not actually what happened, but they did crash a Mars rover because of units. I'll let you do that research on your own time. You guys, I'm not kidding. In our line of work, unit errors kill people. Please keep that in mind. Units are very important. And we have to deal with 2 different unit sets in engineering. So, anyway, let's not get down the soapbox. Let's see how we did. I think I've got the solution here. Feel free to pause this and look at this, but those of you in my class, so yes, let's see here, this solutions manual, I pulled this out of, they just converted everything all the way down to newtons, and they did something silly here. They said, well, kilopascal meters cubed is a kilojoule. Okay, that's true, and that works. I guess it's not really silly, it's just not how I would have done that. But anyway, they took this all the way down to newtons and meters, and then it works out just fine, and they get to the same conclusion we did. Okay, so far, how is that on the screen? That's not terrible. Okay, so far, so good. Okay, so that's part A. Box in your answer. Underline it. Do something with it. Okay. Now let's do this another way. Let's use the generalized compressibility chart. Okay. So if we do this again using the generalized compressibility chart, the Z value, if you will, right? So again, same problem. Example, we're going to do the given information doesn't change. We still have water. I've got a pressure of 3.5 megapascals. I've got a temperature of 450 degrees C, and they want me to find the specific volume value using Z, using the generalized compressibility factor. Okay. Well, so here's the idea there. That's saying, well, PV is equal to ZRT, and then Z basically becomes this conversion factor that improves the ideal gas law. Okay? Now, how do we find Z? Well, as I mentioned, Z is this function of a reduced pressure and a reduced temperature. Okay, so if that's the case, then I need to find those values. So if I find the reduced pressure, that is pressure divided by critical point pressure. And the reduced temperature is equal to the temperature divided by a critical point temperature. Well, I have water, right, so properties, I'll put those over here. And so I have water. That's really all I would need to know to look these properties up. We already know the R value. We said it was if memory serves, 0.4615. We know we're going to need that. That's kilojoules per kilogram Kelvin. The critical pressure and critical temperature I would find in the same table A1 that I just used to find my R value. Okay, so let's see. Water, molar mass, gas constant. The critical temperature of water is 647.1 Kelvin, and it's 22.06 megapascals, 22.06 megapascals for the critical pressure. Steve, where are you getting these crazy values? Well, in our text, that's table A1 in the back of your book. If you're a guest, if you're somewhere else in the world watching my videos, welcome, happy to have you. I don't know what textbook you're using for thermodynamics, but you should have critical point properties for various substances somewhere. You need to go look those up. For us, that's table A1. That's in the 9th edition. That's page 882 in the 9th edition. It's going to be somewhere in the around 900 if you're using another edition. Okay, so what does that mean? Well, that means I can now go find these values. So my pressure is 3.5 megapascals divided by this 22.06. So 0.158, 159, I guess. 159, I apologize. Okay, that's my reduced pressure. My reduced temperature, again, we said that this is 723 Kelvin. 723 divided by 647.1. It's about 1.12, give or take, my reduced temperature. Okay. And then I'll use those in conjunction with the diagram, which is in chapter 3 of your text. Okay. So you go to chapter 3 of your text, and you're looking for this diagram with all the squares and circles and triangles on, and all these curves connecting all these dots. Yeah, it's as silly as it sounds. You're looking for this guy. Right? So I know my reduced pressure is somewhere in here, and my reduced temperature. I don't have a line for 1.12. I've got a line for 1.1 and a line for 1.2. And if I had all the lines in between, this would be solid, and you couldn't see anything. But we know we come in between these two lines and see they get really close, right? So if I'm doing this by hand, I might take a ruler and try to figure out, all right, well, where does 0.16, basically, where's 0.16 in between 0.5 and point here and going here, and I could get pretty close. The best I'm going to do with this chart is probably 0.95, honestly, for my z-value. These intersect 0.16 here, real close to about 0.95. That's probably the best I'm going to do if I'm doing this quickly just off that one chart. Now, because I have PowerPoint, we can do this a little better. I think we can do a little better than that. Okay. So let's see. So far so good. These are the same things. You're welcome to pause this and look at what I've got there. I've just pulled information from the solutions manual somewhere, just to kind of double check what we got there, right? So again, what are we doing? Well, Steve, what the heck are we trying to do? Well, remember, I just need a z-value. So with the z-value, my v-value now is my only unknown. And I said a z around 0.95 is pretty close, okay? We could do a little better. Okay, so go look up R and critical point properties, same thing we just did. And again, we're going to use these two properties, 0.159, roughly what we had, and 1.12. We're going to use that to go find a z-value on this chart. And you can plot, as I said, let's make sure that's showing up pretty good. Is that showing up good? Yeah. So, not bad, right? So I can plot a line of PR right in here somewhere. And then, knowing that in between these two is going to be my TR of 1.12 right up here about where it intersects, and you might could get a z-value 0.96. If I'm doing this by hand, it's probably 0.95, but that's okay. Notice that, I mean, that's really the best you're going to do here. Now, there is in the back of the text, in between, so after the R134 tables and R134 charts in the SI units, there's a couple of these charts. This chart notice that it also has these, instead of just the reduced temperature lines going this way, there's also reduced volume lines going this way. So this is reduced volume 0.7, reduced volume of 0.8, 0.9, and it explains to you how you find the reduced volume. If you know the volume and you don't know one of these two, you know the volume, you could find the reduced volume. Anyway, so there's this chart in the back. Now the advantage to this guy, and I know it's really hard to read, but the advantage is, notice the PR scale. This goes from 0 to 1, whereas back over here, this goes from 0 to 4.5. So this little region right in here is blown up in great detail on this chart here. Right? So you can get a little more resolution. You could actually get to 0.96 here if you took the TR, so you got a TR of 1.1 and 1.15, and go up to where they pretty well intersect, and you could plot 0.16 here, come up here, and you could pretty well find a Z value of 0.96. I wouldn't get 961. This is some solutions manual using a computer program to get to 0.961. But anyway, what do you do with that? Well, again, V, I said earlier, PV is equal to VRT. So once you've got a Z value in hand, your V values are only unknown, and then we got to wrestle with the units again. Again, they're suggesting take everything down to newtons and meters. Take your pascals and your joules down to newtons and meters, and then the units go away easier, and that's true. And so notice what we get there. We get 0.092 when we solve for V. Now, Steve, what the heck does that do for us? Well, if we do a compare and contrast, and if we go to the actual steam tables, the superheated water vapor tables, given a pressure and a temperature, we can go look up in the superheated water vapor tables and see if it's there. And sure enough, we've got a block for 3.5 megapascals and 450 degrees C. You can go look up the specific volume value that matches to that, right? In fact, if you didn't memorize that number, pause right now and go do this. Go find the V value at this pressure and temperature. Go ahead and pause. Okay, so find the specific volume value at this pressure and temperature, and you should get this value for water. Now, how does that help us? Well, compare and contrast there. Part A, just using the ideal gas law, we got this value. Close. Not great, but close. Using a good Z value, really going to the trouble of getting a good Z value, I got 0.92. The property tables, which will give you the property tables will give us the best estimate. They're based on reality. These are based off of estimates and laws. This is actual data. They've actually taken water and measured it with this to verify this value. Okay, so all five of these figures are significant. Here you basically have two significant figures because the best you're going to get on that Z chart was 0.96. So at most you got two significant figures here. All four of these are correct. So the Z value can actually get you to the best estimate if you're careful and you take some time to really get a good Z value. Ideal gas law gets you in the ballpark. Again, it's only an estimate. Sometimes it's a good estimate, but it's only an estimate. Okay. Hopefully that helps. Again, unless the problem statement asks you to look up a Z value, you can if you want to, but I'm not going to require it. Again, I would not use ideal gas law on water or R134. I would never use it on R134 in this class. I would be very careful using it on water unless the problem statement told me to. And then, okay, fine, we'll do it. But you have to know those substances are in the vapor region at a low pressure, pressure below the critical point pressure, for ideal gas law to be useful at all. Okay? And so if you don't have that, you can stay away from it. Again, it's very rare you're going to use R134 in a region where it's anywhere close to ideal gas. Okay, so, but if it's air, oxygen, nitrogen, feel free to use ideal gas law for our purposes in this course. Just understand it's only an estimate, and we could approve it. All right, guys, that's what I got. That is the end of those lectures. Again, I'll put out information about Exam 1 in the next day or so. You guys have a good weekend.